I am Parikshit Ram from IBM Research, and I am presenting our work on the optimality gap of warm-started hyperparameter optimization. In our hyperparameter optimization setup, we have a data domain X cross Y and distribution D from which we get training and testing samples, a per sample loss L, and a model F sub theta S trained on a sampled set S with hyperparameter theta, resulting in an overall loss uppercase L theta D for hyperparameter theta, and the HPO problem is to find the hyperparameter configuration with the lowest loss. SMBO, or sequential model-based optimization, is a standard technique where we first generate an initial design of hyperparameters and evaluate them. Then, until the HPO budget expires, we iteratively construct a surrogate function and a corresponding acquisition function using the hyperparameter evaluations till now, and select the next hyperparameter by maximizing the acquisition function and evaluating it. Finally, we select the best hyperparameter from our evaluated set. This procedure can be computationally expensive for HPO problems with large models or datasets. Hence, in many situations, we need few-shot HPO, where we have a very low budget for SMBO. There is not enough budget for an adequately large initial design, or consequently a meaningfully informative surrogate function. One solution to such problems is to leverage previous HPO experience with different datasets via meta-learning. We usually have some source tasks for which we have available the set of evaluated hyperparameters phi sub t and a surrogate function s sub t for task t. Based on this available information, we solve few-shot HPO on a target task using either a meta-learned initial design or a pruned hyperparameter space allowing for HPO on a much smaller search space, or transferring surrogate functions from source task to target task. Few-shot HPO produces some hyperparameter choice, and in our paper, we study the quality of this few-shot HPO solution in terms of bounds on the optimality gap, which is the additional loss of the selected hyperparameter theta hat over the optimal hyperparameter theta star. Bounds on the optimality gap are characterized with respect to smoothness of the various functions involved, such as the per sample loss with respect to the true label and model predictions, the HP loss L theta D with respect to the hyperparameter theta, the surrogate function with respect to the hyperparameter theta. Another critical component is the quantification of the domain gap, the differences in the losses for the same hyperparameter between a source task and a target task. We present a novel bound for this domain gap between any two distributions D and D prime as a scaled one Wasserstein distance between distributions P sub theta D and P sub theta D prime derived from D and D prime respectively. This derived distribution P sub theta D is a bivariate distribution of the true label Y and the trained model prediction F sub theta S of X on a sample XY from D. The model is configured with hyperparameter theta and trained with set S also sampled from D. There are a couple of important points regarding the domain gap bound. First, the domain gap is hyperparameter specific and can differ between hyperparameters. Second, we can bound the domain gap without requiring a definition of the distance between different multidimensional data distributions of different sizes and domains. A simple one Wasserstein distance suffices. Based on the domain gap bound, we see that the best achievable bound on the optimality gap is of the order of max over theta minimum over the per task one Wasserstein distance between P sub theta D and P sub theta dt. This result implies that if there exists a task T in the set of source tasks such that the target task distribution is close to this task's distribution D sub T, then the optimality gap can be close to zero, implying optimal performance. However, we see that this is not a necessary condition for zero optimality gap. A weaker condition can still allow for zero optimality gap. If there exists a partition of the hyperparameter space such that with each partition the domain gap between the target distribution and any one of the source tasks is small, then collectively This allows for the best achievable overall optimality gap to be zero. Hence, it is possible to achieve zero optimality gap without requiring the target data distribution to match just one of the source distributions everywhere. Given this best achievable optimality gap bound, we first study the optimality gap for hyperparameter space pruning based approaches. The precise bound is presented on the left. On a high level, we have the following insights. Smaller search spaces implying more pruning can help up to a point, providing a precise mathematical justification behind the technique. The best achievable bound is of the order of min over task max over theta, or the one Wasserstein distance between p sub theta d and p sub theta dt. This bound implies zero optimality gap if and only if one of the source task distributions matches the target task distribution everywhere. However, the best achievable bound for pruned spaces is looser than the previously discussed best achievable bound. Note that the order of the max over theta and min over the task is swapped. For the other term in the optimality gap bound corresponding to the size of the pruned search space, we provide precise bounds for schemes that meta-learn the initial design, the bounding box of hyperparameter space, or the convex hull of the hyperparameter space. We also study warm-started few-shot HPO schemes that leverage surrogate functions from the source task. Often, a weighted sum of the source surrogate functions are used to warm-stop the HPO on the target task. In this case, the weights can be fixed across all theta per task as shown here, or the per task weights can be adaptive, potentially varying with theta. The optimality gap can then be bound as posted on the bottom. At a high level, this bound depends on the smoothness and approximation ability of the per source task surrogate functions. The best achievable gap bound in this setting is of the order of the max over theta, a weighted sum over the per task one Wasserstein distance between the target distribution p sub theta d and the source p sub theta dt. Note that this weighted sum bound is not necessarily better than the best achievable bound for the pruned search space schemes. However, a very important insight from our results is that this bound can match the order of the overall best achievable bound if and only if the weights are adaptive and set appropriately, for example as follows, implying that the transfer surrogates do not necessarily lead to better guarantees than pruned search spaces, but they do have the potential to achieve the best possible guarantee if the surrogate functions are transferred appropriately. Thus, to conclude, we present a novel theoretical framework for warm-started few-shot HPO. We use this framework to understand guarantees for existing meta-learning schemes and produce novel insights in terms of the relevant domain gap for the problem and for comparing different existing schemes. Our future directions based on this work include codifying the role of dataset meta features, understanding multi-fidelity HPO in this setup, since that is another popular relevant HPO technique, and leveraging the novel theoretical insights to develop new algorithms. With that, I thank you for your time.